Okay, I am still counting the same number of heads as before. What happens? You guys are waiting for the bus. You could leave already, yeah? All right. Xenon. Now, I am paid to talk about xenon detectors. So, xenon, what do you guys know about xenon? Xenon is a noble gas. That much you know. It's a kind of, it's in traces in the atmosphere. Interesting enough, it was not discovered so much so long. It's like at the end of the 18th century. And it has always still been, so xenon is a Greek word meaning foreign, strange guest. So xenon was already considered a mysterious gas because it was one of the uh, last noble gas, classical noble gas discovered. Now, interesting thing about xenon, atomic number of 54, atomic weight of 131, perfect gas detector. This actually is one big advantage that we will exploit. Things about this, you liquefy it in normal pressure, in conditions of normal pressure at about 100 little degrees Celsius. So it's easy to make it liquid. You can even make it solid if you need to, not so difficult. And you can compress it, of course, as a gas for other things. So more things about xenon. It's used for a number of commercial applications, including lamps, including electronic industry. There is a number of applications for xenon. But now, let me tell you things about production of xenon. So you could imagine a normal commodity is a commodity in which demand and supply are connected. All right? Take anything that you want. Any commodity that you want, if, let's say, if there is a lot of production, more than demand, then the prices go down. If there is a lot of demand, then the prices go up, and the market regulates automatically because of this demand versus production system. Now, xenon is not like that. Xenon is produced as a byproduct of air liquefaction. So, who needs air liquefaction? Steel factories, steel mills, big steel mills. Okay, those big steel mills need a flux of air to cool down, and so they process so huge quantities of liquid air that you can extract the tiny fraction of xenon, and this is relatively so extracting xenon and krypton on the same purification process is kind of doable. All right, and then you still will need to separate. So this is nitrogen, this is oxygen, this is argon, and the invisible part of the pie is all the rest, all right? So you still need to, first of all, separate the part, and then you need to separate xenon from krypton, okay? So one, that gives you a production bottleneck. The first thing to understand with xenon is that demand and supply are not connected. So what is connected is demand of steel with xenon production. But maybe you find a magic application of xenon, you start to demand, and then there is no more xenon because nobody's asking for more steel, so xenon prices go up. The second thing to understand is that the number of factories that can refine xenon are limited. There are so many steel mills in the world, these are big things. Then so many factories, and that means that the market is kind of toppled. So that translates in the following way. Before the Russian-Ukraine war, the market was kind of stable, was growing little by little. And companies thought, okay, I can do a little bit better next year. The global production, world production of Xenon was about 65 tons per year, and it was growing at a rate of about 2 tons per year. Now, 65 tons per year, you will see later that the Nexo experiment wants to get 55 tons of enriched xenon. Enriched xenon is 10%. So Nexo is already saying, I want the world production, 1 year world production. But the dark matter experiments, future dark matter experiments, they want at the very least 1 year of world production, maybe 2. So that should be sufficient to tell you that we travel again. You say, give me the whole world production for a year, all for me. Guys, don't do anything else with Xenon. Oops, difficult. Now, that was difficult before the war. But then the war came, so here's production of countries. Now you can see that the Chinese are sort of dominating the game, but this is why. This is because this is what used to be before the war. So before the war, you would get 22% of the total xenon and 25 from Ukraine and Russia. So half of the world, half of the xenon in the world was produced by these two guys. And they were actually collaborating and working together on that. The way we found, in the next experiment, also Nexo, also Cadenas, we all got our enriched xenon about between 10 and almost 20 years ago. The way we all did, in different ways, ask me about that later on the evening. First, because otherwise I cannot confess some of the fine points of working with the Russians. But in different ways, we all did the same. We talked to the Russians who talked to the Ukrainians. The Ukrainians were the producers. Typically, they produce 1 ton of xenon, which went to an enrichment plant in Russia to produce 100 kilograms of enriched xenon for NEX, 200 kilograms of enriched xenon for EXO, and almost 800 kilograms of enriched xenon for Cadenas. So in total, a total of 1 ton of enriched xenon was processed, again, more than 10 years ago, which implied to move around of natural. And all that was done quite easily and not very expensively, in relative terms, by the cooperation. Actually, they were working together between industries in Russia and Ukraine. All this is gone. And with all this gone, all this is gone. So we're in trouble. You have heard this a number of times. Is the economy stupid? Right? Producing xenon implies that you need to have consumers of xenon, and consumers of xenons, in spite of the fact that the market is pretty high, the price changes a lot because of the production. And this is today. You see that the demand is going up. The supply is stable. So in spite of the work, things are not dropping brutally because of other players, China in particular, playing it, but certainly it's not keeping up with the demand. And of course, you know that the demand before the war was in an exponential rise. And with the war, it flattens. And it flattens because everybody understands that there is no xenon available. So the war has been a big disaster for the xenon market in general, for technology in general, and for neutrino-less and dark matter experiments in particular. And here is the really sad thing. If you would do the experiment in 2017, or you would buy your xenon in 2017, it will cost you about 5 euros per liter. In 2023, it would cost you 50. So it went up an order of magnitude. Now, this doesn't imply that it's going to be up forever. Actually, it's already going down. Right now, it's volatile, meaning that depending on who you talk to and the data you ask for it, your prices can range from factors 2, 3, 4. This, by the way, is not the problem only on the xenon people. Everybody who is doing neutrino-less elevator experiments are in the same situation. The field did rely a lot on Russians to do the enrichment, and the consequence of the war and the vetoes and this and that is that science is paying a big price. All right? In the case of xenon, as you can see, also big price. So we have kind of two issues to think in realistic terms. First of all, the total production of xenon is order 50 tons per year. So future experiments who want to get the whole production of xenon need to figure out how, even if xenon is back being cheap again. And second, even if xenon is cheap again, and even if xenon production is okay, you still need to enrich it. And the only guys who knew how to enrich xenon industrially were the Russians. So if you keep in war with the Russians and angry with them, we're in trouble. So this is the real world kicking into the science world. All right, now that we know everything about xenon, let's talk about the xenon properties. What happens if you have xenon and a charged particle goes around it? Boom. Well, it can happen that it excites one of these electrons to an upper charge, right? And then it will eventually de-excite and emit a photon. So the process typically is that you get your excited xenon that reacts with another couple of xenon atoms. You form what you call a dimer, which is a sort of molecule, excited molecule, and then this molecule de-excites again by emitting ultraviolet light. This ultraviolet light actually two things can happen. The electron can escape and nothing happens, and then you have a little bit of charge signal or information loss. And this situation corresponds to what we call the Fano factor. Fano factor is what is the intrinsic fluctuation that any material, in particular xenon, will have because of this charge information, this charge loss, this information loss. Now, we know that germanium has incredibly good Fano factor. So good that 0.1% resolution, full width at maximum. By the way, here, stop. Everybody in the field of the generalized elevator decay experiment talks about full width at maximum. Everybody in dark matter used to talk about full width at maximum. Then along came the EXO and then NEXO guys, talking always about sigma. The result is that now you need to think twice when you hear a resolution. There's a 2.2 factor, 2.3 between them. Be careful, okay? Which resolution we are talking about? Germanium people always talk about full width at maximum, just because they are, if they quote in sigma, the number comes too small. 0.1%, it means that the Fano factor of germanium is extremely small. What about xenon? We'll come back to that, okay? But notice that clearly we have a mechanism for energy loss, right? Now, instead of this, we can have the production of light, as we have discussed, and notice that we have like two kind of mechanisms, and this is important. You can ionize the xenon, then produce xenon plus electron, and then this electron can recombine, and then you go to the scintillation or escape, and then you go to charge loss, right? So notice that one of the things I can do with xenon is because I'm ionizing it, I can kind of put an electric field and take my electron someplace and measure those electrons. This would be a measurement of the ionization, and it should be proportional to the energy. And it should be some loss, as we have discussed, and that will give me a Fano factor for that particular effect, yes? Now, the other thing that the xenon will do, no matter what, it will scintillate, because I will have these dimers that will decay, and these dimers will give me ultraviolet light, which actually has two lifetimes. One triplet at 27 nanoseconds, one very fast singlet at 2 nanoseconds. Message of that, the scintillation light of xenon is pretty fast, right? Even if you put an electric field and then you prevent recombination, you never get more than maybe 35 or 40 nanosecond scintillation. So you have a quick signal that comes from scintillation. Can you measure the energy from scintillation? Yes. It depends on how much scintillation you have. But you have two ways in your hand now. You have quick scintillation, and then you have the possibility of measuring both in scintillation and ionization the energy. All this come about, why? Because xenon is a noble gas. And then when you ionize the gas in electrons, the electrons will not recombine. Beautiful. If it could not be a noble gas, we would be in trouble. Second thing, because xenon is transparent to its own ultraviolet light. Beautiful. Otherwise, the light would scatter and we would not measure it. So xenon was put by God so that we could make these measurements, right? And if you believe that, then you have at least a religious reason to do these experiments, which is important. All right, so we have xenon. Xenon was put there for some high power so that we could do the experiments. Now, tell me about ionization and scintillation. Obviously, they should be anticorrelated, right? Because what goes to ionization doesn't go to scintillation and the other way around. And this anticorrelation is extremely useful. We will see later why, but let me make a spoiler already. Without the anticorrelation, we could not do liquid xenon experiments. We'll see why in a second. Keep that in mind, though. Now, we have seen that, but the other thing, we have seen that xenon scintillates, ionizes, charge will not recombine, light will go through. So it's a good detector medium. But it turns out to be a good target medium too. Why? First of all, because Q beta beta is 2.5 MeV. So it's away from almost everything. Very key. Maybe the highest power thing is not so that, because we have a background of a gamma only 10 keV away. So I have two explanations for that. One is that there was not put there by a high power. The other is that there is a second high power, which is trying to make life equally difficult for us. And the competition of both of them is reality. So except for that gamma and another one of thallium at 2.6 MeV, xenon is pretty decent. Now, when it comes to, where is xenon here? When it comes to here, to phase space, it's kind of fine. Run of the mill, good guy. When it comes to nuclear matrix element, fine. You know, not the best one, not the worst one. The one with more errors, not the one with less errors, it's fine. So actually, it's a good element, it's a good isotope. Which brings me to something that probably has been mentioned, but I want to mention again. Suppose that you are a funding agency and you need to decide how many experiments you want to fund. What would you do? Would you fund just one isotope? 2, 3, 7, no? Ideas. Let's take a second for that. I could come with the argument, look, this is my first, I have the best isotope in the world. Please fund me. With what we saw yesterday, in the previous lecture and this lecture, you should know already the answer to that question. How many experiments do you want to fund? I mean, let me make this question simpler. One or more than one? Why? Say it louder. This is a general thing, but a more specific thing. This is a general argument, but give me a specific argument. Exactly. This is the way first of all, the physics of the isotopes are different. Suppose that you just choose one and you get signal. How do you know there is not a kind of systematic error that nobody's checking? So it's kind of, but suppose that you don't get signal. How do you know it's not just pure bad luck and the nuclear matrix element killed that poor guy? So physics tells you, hey, don't put all your eggs in the same basket. But also technology, as we will see, tells you, don't put all your eggs in the same basket because different isotopes allow for very different technologies. So this is the reason why the field is now moving into kind of at least 3 isotope thing. And if you remember the baseline of our problem, 1 background event, maybe 0.1 background event per year on the right, it would be crazy not to do it. Okay, so keep that thing in mind. Is there a competition between the different isotopes? No. There's no competition. This is what we like to tell the funding agencies so they give us more money. There's no real competition. There is absolute necessity of using several isotopes to do these experiments. There is no way around it. Is that clear for everybody? So let's move on. As I said, now there is a few other things nice about Xenon, by the way. First of all, there is no long-lived radioactive isotopes. So it's not like argon. So it's not giving me trouble. Okay, when you activate with cosmological with neutrons, they also tend to decay. They don't stay there forever. So actually, you can make it extremely radio pure. You can filter all the radioactive krypton away. So it's a really nice stuff. And it has another kind of interesting thing that we will touch in the last day. It ends up in barium 136. And barium 136 is an interesting metal. You could be crazy enough to decide that you can detect barium 136 as a way of being sure that you have neutrino-less double beta decay. In case you didn't understand, I am stating that some crazy people think they can detect one barium 136 isotope in 1 ton of xenon. Well, there is not only one bunch of crazy people, there are 2 bunches of crazy people actually. The crazy liquid people who say, oh, easy, 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 and then the crazy gas people that say, oh, easy, easy, and then the chemists of the gas people, they are the worst of all. Okay? So we'll come back to this and to the kind of games that you can play in this game later in these lectures. So this lecture has only one exercise. You have the graphs there. Just compute how much money you need to pay for your Xenon experiment. If you can do the experiment before 2017 or last year. Okay? And I think this is just in time. At the end of my second lecture, I think we can stop here. We'll carry on tomorrow. Thank you.